Hi, in this video we will introduce the notion of similar matrices. This is a relation between square matrices, and then we will study some examples and some basic properties of this relation. Let us start with the definition. First thing is that we consider square matrices. So let A and B be n by n matrices. Then we say A is similar to B, and we denote it by, so the way we denote is A tilde B if, so the definition is that if we can find a square invertible matrix, if there exists an invertible matrix P such that when you multiply P from the right to A and the inverse of P from the left to A, we get B. So if we sandwich A between the inverse and the inverse of P and P itself, we get a B back. Well, this is a relation, and usually checking this is not easy, but let's see some examples in which we will do some kind of work related to the similarity. Okay, so let me start with this one. Show that the matrix, so here is A, is similar to B. Well, if you don't have the last hint that given there, this is not easy to do. We will study more things and you will see how this works. But in general, it's not easy. And well, here P is given. So we need to check. So we need to check that if we multiply P to A from the right and P inverse from the left, we get the matrix B. We need just to check that. Okay, so here, P is that, this is 2 by 2 matrix. P inverse, we know how to find P inverse. It's easy. Just interchange entries on the main diagonal, multiply off diagonal entries by -1, and 1 over the determinant. So 2 times 1 minus 1, it is 1. So now if I multiply P inverse 1, -1, -1, 2 from the right to matrix A, and from the left to matrix P itself, let's see what we get here. So first I will multiply the two last matrices. So this one will give us 1, 0 times 2, 1. This is 2, and this is 1. 3, -2 times 2, 1. This is 6 minus 2 is 4. And this is 3 minus 2 is 1. 1, -1 times 2, 4. This is 2 minus 4 is -2. 1, this is 0. -2 plus 8 is 6. And -1 plus 2 is 1. And as you can see, this is B. That means that, yes, we showed that these two are similar. So A is similar to B. The second example says, find all n by n matrices such that the identity matrix is similar to B. Well, let's see. I similar to B means what? Means that there exists an invertible matrix. P such that when we multiply P inverse to identity and then multiply by P, we get the matrix B. But this is identity matrix. We know when we multiply identity matrix to any matrix, we get that matrix. And we multiply any matrix to its inverse, we get identity matrix. What we showed here is that the only matrix which is similar to identity matrix is the identity matrix itself. Well, just for a special case, we will see that this in general is not easy to determine these things, but for identity matrix it wasn't bad. Okay, let's do another example. Show that 1, 0, 0 is not similar to any matrix of the form x, y, z, and minus x. Why is that so? So let's assume that this is true. So 1, 0, 0, 0 is similar to x, y, z, and minus x. What does this mean? This means that there exists an invertible matrix P. So invertible matrix. Well, it is 2 by 2 matrix, yes? So I will write just A, B, C, D. And to be invertible, it means that what? AD minus BC is not equal to 0. Okay? And then from there, right away, you can say that, oh, what is P inverse? P inverse is 1 over AD minus BC. dA, interchange the main diagonals, multiply off diagonals by negative sign. So from this, then we conclude that P inverse 1, 0, 0, 0 times P, which is A, B, C, D, this is going to be equal to x, y, z minus x. Okay, let's do the computation for the right-hand side. Left-hand side first. So this 1, 0 times that will give us A, and then B, then 0, then 0. And P inverse is actually 1 over AD minus BC. This is D minus B minus C and A. Well, let's multiply that part. So this will be 1 over AD minus BC. So this is DA. This is DB minus CA and minus CB. So if our assumption is true, then this will mean that this is x, y, z minus x, yes? This is by our assumption that left-hand side is equal to right-hand side. But what does that mean? That means that the corresponding entries are going to be the same. So here, one entry on the left-hand side is DA or AD over AD minus BC. This is supposed to be equal to x. And also two entry of the left-hand side is minus BC over AD minus BC equals to minus x. The reason I'm picking these two is that the entries on the right hand side, the only two entries that have relation are these two ones. I want to use that kind of a relation here. Now, you notice that the numerators of these two guys, if if I add, I get actually the denominator. So that's why I will add both equations. That will give us AD minus BC over AD minus BC, and that is supposed to be x minus x. Well, we assume that AD minus BC is non-zero. That means that this left-hand side is going to be 1, and right-hand side is going to be 0. Oh, that cannot be true. And what was the assumption? The assumption was this, so that means that these two 1, 0, 0, 0 cannot be similar to any matrix of that form. Okay, so all doing these things, there are some properties of similarity. I want to go over those ones. First thing is that fact one is that every square matrix A is similar to itself. This is called that the relation is reflexive. Everything is similar to itself. Why is that so? Well, it means that I have to be able to find a matrix, invertible matrix. When I do P inverse A P, I get A back. Well, that matrix, it's enough to set P, the invertible matrix, to be matrix, the identity matrix. Remember, the identity matrix is invertible, and the inverse of that is the matrix identity itself. So if you multiply P inverse AP, you basically have I, which is A. And that's what it means. A is similar to itself. Fact 2, this is called a symmetric relation. It says that if A is similar to B, then B will be similar to A. So you don't need to be worried about saying which one is similar to which one. If one happens, the other one is also true. So that's why we say A and B are similar instead of saying A is similar to B and so on. And why is that so? So A is similar to B means that we have an invertible matrix P such that P inverse AP is equal to B. Now I want to do something here. I will multiply this equation, both sides, by P inverse from the right, and by P from the left. So we'll get P inverse AP, and P inverse. And then the right hand side will be P inverse. Well, you simplify these ones, these are inverse of each other, so this will give us A. The left hand side is going to be A. Right hand side is P inverse. But you have to be careful, because the definition of similarity says that inverse times A times the matrix, the invertible matrix. This has P inverse. Okay, but it is enough to set Q to be P inverse. Why did I do that? Because you see P inverse then is equal to P inverse to the power, inverse of inverse is P itself, and P inverse. And then this is Q, so Q inverse is in the left, and Q itself is on the right. This is equal to B. That means that B is similar to A. And the last fact, I will call it fact 2. It's called transitivity. So if A is similar to B and B is similar to C, then you can conclude that A is similar to C. Well, this is also straightforward, because you see if A is similar to B, that means that we have P inverse A P equals to B for some P. And if B is similar to C, we can say that there's an invertible matrix Q such that Q inverse AQ is equal to C. Now, this must be B, sorry. Yes. Now, you multiply this thing by Q from the left and by Q inverse from the right. The other way around, Q inverse from the left and Q from the right. Then it will be Q inverse P inverse A P Q equals to Q inverse B Q. But we know that Q inverse BQ is equal to, sorry, let me just write this. This goes there, is equal to C. What we have here is that now we have Q inverse P inverse times A times PQ is equal to C. Well, if I set it is enough to set PQ to be my new matrix, I'll call it R. And then R inverse, it is invertible because product of invertible matrices is an invertible matrix, and this is Q inverse P inverse. So that means that what we showed is that yes, there is an invertible matrix R such that R inverse AR is equal to C. So these are three properties. Why did I put fact 2? This is fact 3 here. Yes. So these three properties are the properties of that relation. And while in general checking similarity is not easy, in the next video we will find some good facts to help us to find similarities for some matrices.